Accidental explosions give no warning. They can bring death or lifetime injury. Each laboratory worker knows the need for safety shielding in chemical laboratories. We firmly believe that the academic laboratory can be one of the safest places in which to work with the proper shielding devices. Implosions of low-pressure equipment, such as Dewar flasks, spell possible danger. Here, too, the chemist must have special shielding to protect himself. Many accidental gas explosions in academic laboratories have been mixtures of hydrogen and oxygen. For experimental purposes, the explosions can be sharply triggered. The explosion range is very wide, but for our experiments, the proportion of hydrogen and oxygen in water was used. The gases are easily measured by water displacement. The slow motion picture shows more clearly the violence of the hydrogen-oxygen explosion. In this case, all movable objects were swept away except the wash bottle. The shattered ignition assembly dropped back from the ceiling, while the eudiometer slowly fell away from the explosion center. Any seasoned teacher can recall many case histories, some tragic, some fantastic escapes. This case history is a typical part of a hydrogen experiment. The nearest freshman removed her safety glasses. Apparently, her apparatus had not been checked or the generation of pure hydrogen verified before she lit the burner. She suffered the loss of one eye. The other two students were not hit by the widely scattered missiles. In this case, the student added sodium shavings to vanadium oxytrichloride. The inside surfaces of the hood were covered with corrosive liquid and bits of burning sodium. The student was not hit. In case history number 3, magnesium perchlorate was used in the organic preparation on the left. Both students were wearing substandard safety glasses. The student on the right was not hit, but the explosion on the left demolished that apparatus and destroyed one eye of that student. The research chemist in case 4 used a steel spatula in transferring his perchlorate preparation into a wide-mouth storage bottle. He had not provided any kind of shielding. The violent explosion badly mangled his left hand and caused fatal internal injuries. He never regained consciousness and died the second day. To better understand the erratic nature of laboratory explosions and some fantastic escapes from glass missiles and splashes of corrosive liquids, a plan was instituted for charting the explosions. The charting paper was sensitized. After each explosion, the torn parts of a chart were assembled on the table and repaired where necessary with transparent tape. The chart was then attached to an easel. Holes are easily detected against a dark background. In all the charting experiments, no two identical charts were ever discovered. The distribution of missile hits and splashes appear to be totally unpredictable. Color depended on combination of solutions used. To make this study more realistic, the chart was replaced by sensitized papier-mâché masks equipped with eye and face shields. The explosion flask was centrally located as before, and a suspended body shield was placed across the opening. The erratic nature of the explosion was quite evident by the wide difference in impact of splashes and glass missiles. The left lens of a safety glass was shattered, but was not blown loose. 8 selected masks with shields removed show the difference in protection by comparison with number 0 mask, which had no shield. Safety glasses on 1, 2, and 3 allowed some spray to reach the eyes. Goggles 4 and 5 offered surer protection. The face shield on mask 6 had a short window, thus exposing the lower part of the face and the neck. The penetration of the neck by a large piece of glass should convince us that an adequate face shield should cover the entire face, scalp, and neck. The shield on 7 had an 8-inch window. The wide coverage on number 8 displayed the most desirable protection. We turned 8 masks with the same shields through 90 degrees to show the protection offered from the side. The side attack from the explosion resulted in some spray reaching the exposed eye of number 1 and of number 2. The solid side shield on number 3 stopped the spray. Of the goggles, the one on number 4 with perforated sides allowed some spray to pass. The solid sides of goggles on number 5 stopped the spray. The narrow windows of the face shields on number 6 and 7 exposed the ear canals, while the very wide window on number 8 offered full protection. Our selection of eye shields must be primarily for protection of the eyes. Many devices are on the market, ranging all the way from some lightweight visitor's glasses to the standard safety glasses and the more protective goggles. Safety glasses may be plain or supplied with perforated or solid side shields. Goggles are typical designs. The ease of wearing goggles consistently depends very much on proper fitting. This student is adjusting the elastic band just firmly enough to gently hold the goggles in place. Our selection of a face shield depends on the type of work to be done. Some leave much to be desired for coverage of the whole face. This student has chosen a sturdy shield with easy adjustments for height and circumference. By proper adjustments, he has made it as comfortable as his old hat. We will cite but one case history of an implosion accident. A biochemist was fatally injured when his suction filtration flask imploded. This slow-motion picture shows in detail one imploding suction filtration flask. Implosion of a Dewar flask can be dangerous as the sharp, heavy fragments move away from the implosion center. In this case, the graduated cylinder, the wash bottle, as well as the mannequin face were pelted by the large fragments of glass. Watch the red stopper. A Dewar wrapped with electrician's tape is a safer flask. Shattered walls were quite well contained. To carry on a chemical operation without sufficient shielding of the body as well as the face can be very dangerous indeed. The chances of complete escape from injury are quite remote. The eyes, face, and neck are vulnerable. Heavy glass missiles can cut through ordinary clothing. Shield A has a laminated glass window and a light metal base. In slow motion, this same event shows more clearly the violence of the number 4 charge explosion. The flask was completely demolished. The liquid and shattered glass were hurled against the shield with such force that it was tipped beyond the point of balance. This poorly balanced body shield struck the face shield and scratched the window as the mannequin was struck down. The face shield prevented a severe blow to the forehead and nose of the mannequin. The impact would have registered severe bodily injury to a live subject, especially if only safety glasses had been worn. 4 kilograms are added to the heels of Shield A. The stability was greatly increased, as shown by this slow-motion picture. This study could be extended to include variations and positioning of added weights. Added weight increased the stability of Shield A, but the unprotected window on the left withstood but one blast. This display shows in the center a Lexan sheet which protected the laminated glass on the right during 6 explosions. This 1/4-inch plexiglass shield, mounted in a heavy lead base, is a stable shield to begin with, but can be made even more stable with added weights. This custom-built shield, suspended from a track on the ceiling or from rods, occupies practically no workspace and has the advantage of swinging out at the bottom. It cannot tip. What are the requirements of a good safety shield? This visitor's glass was described as light and comfortable. One lens was blown out and the other cracked. Here we show only the results of the explosion. This pair of much heavier visitor's glasses with solid side shield offered good protection for the eyes. This visor-type goggles withstood a mild explosion remarkably well. It can be worn over prescription glasses very comfortably. This substandard 20,000th inch window on a face shield for general purpose is inviting tragedy. This demonstration should convince us that only the minimum standard 40,000th inch window should be considered. This comfortable, very long and very wide shield, with thickness in excess of the minimum standard, withstood the same number 3 charge explosion. We can hope that these specifications are accepted as the minimum. Potential danger lies in all laboratory explosions and implosions. We firmly believe that with proper shielding at all times, the chemical laboratory can be made one of the safest places in which to work. Much safer than the home, and far safer than our highways.